Swayam Prabha. Digital India. Educated India.
What we shall be studying today is the duality and complementary slackness. These, as we have already seen the concept of duality and the essential idea of primal versus dual. Suppose we write in a matrix form, then that matrix form would look something like this. We know certain very important matrix in linear programming formulation. First of all, the C matrix. The C matrix is the profit matrix. Is it all right? C matrix is the profit matrix, the profit coefficient associated with the individual, the unknowns or the decision variables, which is known as the X. So supposing there are three variables x1, x2, x3, and there are three profit coefficients C1, C2, C3, then maximize Z equal to C1 plus C2, x2 plus C3, x3. So in a matrix form, we can write Cx. You could have written C transpose X also, where both C and X are column vectors. But here we are, for the sake of simplicity, we have defined B and X as column vectors and Y and C are row vectors. So if you define C as defined as a row vector and X as column vector, then maximize Z equal to Cx is the matrix representation of the primal objective function. And we know the standard form of maximization problem. All the constants are of the form Ax less than equal to B, where A is the coefficient matrix, X is the decision variable, and B is called the values, or these are basically the resource quantities available, right? So B is the resource quantities available. And usually for a maximization problems are type of product mix problem when there are several resources which are competing, and all the resources are required to produce all the the products which is represented by the X. So Ax less than equal to B. That is the standard form of the in the matrix way of writing the constraints, and X is greater than equal to 0, which is our non-negativity constraints. So, can you convince yourself that if we take the dual of these, then a set of dual variables y associated with individual constraints, then it will take this form? So please spend some time, a little bit of time in going through the primal and try to find its dual. And please convince yourself that the dual would look like what is written there. You see, the individual constraints, they are associated with a dual variable y. So B into y, it is since it is written as a column vector versus row vector, so we can write as yb. Why it is yb, where y is a row vector, then you can see that supposing there are suppose there are 4 constraints, there will be 4 dual variables. I have already told you that there are 3 decision variables X, so 4 dual variables Y, because there are 4 constraints. So obviously there will be 4 B values, the resource quantities. The B values are also going to be 4 in numbers. So it will be 4 into 4. So, if you write Y is a row vector, which are 4 numbers, and B a column vector, which are also another 4 numbers. So a row vector multiplied by the column vector, it will be your objective function. Minimize W equal to YB. The constraints on the other side, you have to see from individual equations, and you can see that C is going to be on the right hand side. C is going to be on the right hand side, and it will take a form of YA. greater than equal to C, is it not? So YA greater than equal to C, that will be the corresponding dual constraints. Now, since all the variable of the primal, they are greater than equal to type, so therefore all the constraints will be greater than equal to type because it's a minimization problem. And since the primal problem is in standard form for maximization, all the constraints are less than equal to. So the dual variables y should be all greater than equal to 0. Is it all right? So I hope you have understood that how these dual form and the primal standard form are actually written and what are their corresponding significance. Is it not? So once we have known these, let us see these example. These example we have already seen many times. We have solved also the original problem. Maximize z equal to 600x1 plus 400x2, subject to 4x1 plus 3x2 less than equal to 360, 2x1 plus x2 less than equal to 160. 2x1 plus 3x2 less than equal to 300, and there are non-negativity constraints. So we have seen that if we take its dual, the y1, y2, y3 are the corresponding dual variables, and the objective function will be, this is yeah. So objective function will be connected to the resource values. Those are the B values. So 360 y1 plus 160 y2 plus 300 y3, minimize that will be your objective function. And these coefficients, that is, see how the coefficient matrix 4 3 2 1 2 3 is now written in the reverse order, the A transpose way. And so therefore that is how it is in the previous this thing. It was it is written as YA because Y is a row vector, so A is on the other side. So that form would be then 4y1 plus 2y2 plus 2y3 greater than equal to 600, and 3y1 plus y2 plus 3y3 should be greater than equal to 400. And x1, x2 will be the corresponding dual of the dual, which are nothing but the primal. Now, once again, I want to remind you that because these non-negativity constraints are like that in a standard form, that is why the dual constraints are greater than equal to. And since the primal problem, all constraints are less than equal to, that is why in the dual problem we have greater than equal to kind of sign. So now that convinces us, and once we are convinced about this particular form of putting equations, then we can look at some of the very important dual theorems. There are 4 theorems. In fact, the first duality theorem is known as the weak duality theorem. So let me read out the weak duality theorem. For symmetric primal dual linear programs, the value of the objective function of the minimum problem, that is the dual, for any feasible solution is always greater than or equal to that of the maximum problem, the primal. In other words, the YB should be always greater than equal to CX. So you see, the first thing to note here is that the symmetric primal dual linear programs. So first of all, there should be symmetric in nature. Symmetric in nature here basically mean that they should be perfectly balanced. Yeah, is there any question? So the primal dual linear program, the value of the objective function of the minimum problem. So here there are 2 problems. One is the maximum problem, which is our primal. Another is the minimum problem, which is the dual. Is it not? Now for any feasible solution is always, now see, look here, when you are solving a primal problem, it goes through, it is not that we get only the optimum solution. We get a number of solutions while solving the maximization problem. Isn't it? It goes through several steps. And if you know very well the feasible corner point solutions, they are the candidates or which are called our basic feasible solutions. When you solve LP, which corresponds to the feasible corner point solutions graphically. They are the candidate solutions and optimal solution is one of them. Usually we start from a point, we go to another point by keeping feasibility and looking for optimality in the primal. And once we get to that point where all the points in the vicinity are no better, then we know that we have reached the peak because of the hill climbing technique we follow. And that point would be our optimum point. So, that we already know that method. Now the question is that supposing we are in one of those feasible points, is it not? One of the feasible points in the primal, and there is another such feasible point in the dual, which may or may not be the optimum. Then what is being said is that the YB will be always greater than the CX. Is the thing clear? Okay, let me explain it with a graphical thing also. You see, this is a solution, but the solution is not. Let's look at the graphically. How do we solve this particular problem? So the problem is maximize z equal to 600 x1 plus 400 x2. Is it all right? And how do we solve graphically? We take all those constraints, that is 2x1 plus x2 equal to 160. So since 2x1 plus x2 is less than equal to 160 in our case, so this side is our solution space. Similarly, 4x1 plus 3x2 equal to 360 is this line, and 2x1 plus 3x2 equal to 300 is this line. Now for each of those three constraints, the solution space is towards the origin. So that gives us a solution space OABCD. Isn't it? So OABCD is the solution space. Now question is that we see here that C is the optimal point. Right? C is the optimal point, no doubt in that. Now C may be the optimal point, but what about the other points? The point O, point A, point B, point C, point D, all those points. The Z value of O is 0 at origin, 40,000 at point A, 50,000 at point B, 52,000 at point C, and 48,000 at point D. So at different points, the values are different, but the highest possible value is returned at the point C. So, if you really look at and analyze these, then you find that the objective function value improves as you, iterate more, and ultimately the optimum value in the maximum is the highest possible value. Isn't it? The highest possible value which is returned at the point C. So I hope this point is clear to you that how this thing happens. And now look at the dual problem. The dual problem is this one is our dual problem. Minimize y equal to 360 y1 plus 160 y2 plus 300 y3 and subject to those constraints. Now we see the optimum solution here is Z also 52,000. So both the optimum solutions are equal at that point. But what about other points? Supposing I take some other in between points, then the value will be more than 52,000 or less than 52,000. That is what is the essential point. So at other feasible points, which actually solves these two equations, supposing I take y1, y2, y3 suitably higher, and by taking suitably, say for example, suppose I take instead of 100 100 0, suppose I take 100 100 100. Then what you get is 4 plus 2 plus 2, this value quantified as 800, and this value quantifies as 3 plus 1 plus 3, that is 700. that actually satisfies both the constraints. And thereafter we have, but that is definitely not a basic feasible solution. Yes, So other basic feasible solutions in this particular minimization problem would be, values other than that, but those values will not be possible to find out straight away. Yes, So anyhow, that we can see, and one thing is clear, that those values, the Z value will be always higher. So what is happening? In the original problem, that is the primal problem, the optimum solution is the highest possible, and in the dual problem, the optimum solution is the lowest possible. But those two values are equal. Is it not? In the primal problem, which is maximization, the value is 52,000. And in the dual problem minimization, optimum solution is again same 52,000. Both are equal. But in the original problem, it is the highest possible value. And in the dual problem, it is the lowest possible value. So if you understand this, now once again read this weak duality theorem. For symmetric primal dual linear programs, the value of the objective function of the minimum problem, that is the dual, for any feasible solution is always greater than or equal to that of the maximum problem. That is, YB is always bigger than or greater than equal to CX, right? So it's a simple thing. It took us time to understand exactly what it is and what is the meaning of this. But the weak duality theorem essentially clearly states how the objective function values of the two problems, the primal and the dual, are related to one another, and how the minimum problem always returns a greater value. So that we already seen with the help of an example problem, and trying to go through the different basic feasible solutions. Here only thing that means by symmetric is that, like primal to dual, if you convert the dual of the primal, you get the dual. Similarly, if you take the dual of the dual, you get back the primal. Okay. Is it not? So in that sense, it is symmetric. That means the primal can be dual and dual can be primal. Correct. So from that point of view, we are seeing it. Now, there are four corollaries of the weak duality theorem. So what are those four corollaries? Let us look at it very carefully. The first corollary, which states the objective function value of the maximum problem for any feasible solution is a lower bound of the minimum problem objective function. You see, what is a lower bound and upper bound? See, these are going to be very important concepts later on when we are going to, talk about bound method. Usually, supposing there is a particular problem and we cannot find its solution straight away. But see, there could be a quick way of finding the lower bound or the upper bound, which is going to help us in some way. Say, for example, you are given a matrix, is it not, which are distances from, 4 points to one another, A, B, C, D. So if you look at the minimum possible distances, right, A to B, B to C, and C to D, which is immediately clear from those specific values. It is sometimes easily possible to find some lower bound of distances. Is it not? So supposing if you find what is the lowest possible distance from A to B, what is the lowest possible distance from B to C, what is the lowest possible distance from C to D, so that would give, because of such thing, that if you have to go from A to B to C to D, you can quickly find out what is the minimum possible value by which you can make that particular travel. So that would give us a lower bound. So similarly, supposing you have given a minimization problem, and You know very well that the solution space is in the first quadrant, bound by the x1 and the x2 axis. You can quickly know that a lower bound of these solution to the minimization problem is going to be 0, 0. It doesn't mean that 0, 0 is has to be a valid solution and it has to come out as the optimum solution. No, but it provides a lower bound, right? That you know very well that lowest value cannot be below that point. So that is usually called the lower bound, right? So have you understood that? And similarly, there is an upper bound that the value cannot be beyond that point. So therefore, the first corollary says the objective function value of the maximum problem, that is the primal, for any feasible solution is a lower bound of the minimum problem objective function. Very clear, because the minimum problem values are always higher, and at the optimum point they are equal. So therefore, if we find a maximum problem and we find any feasible solution, we know that the minimum problem cannot be solution cannot be any better than that, right? It can be even worse, but uh, not any better. Similarly, the objective function value of the minimum problem for any feasible solution is an upper bound of the maximum problem objective function. So in the last example, let's go back to that example once again. In that example, we see that for the minimum problem, suppose a particular solution is 55,000. We can tell that this 55,000 is an upper bound of the maximization problem, because 55,000 may not be optimal for the dual problem, but we know this much, that at the lowest the value that we get for the minimum problem solution is going to be the best possible of the maximization problem. Therefore, that 55,000, if it is optimal, well and good, but if it is not optimal, even then it will serve to provide an upper bound to the maximization problem. Similarly, the maximization solution will give a lower bound to the dual problem solution. So I think these are easy to understand, and these are the two corollaries which are coming out from the weak duality theorem to begin with. We can only comment about the minimum possible value of the minimum problem and maximum possible value of the maximum problem. That is all we can say. Between the primal and the dual, usually what happens, the maximum possible value of the primal, which is maximization, and the minimum possible value of the dual, which is the minimization, they becomes equal. And that is the optimum point. So one is coming from the lower side, the other is coming from the upper side, and where they meet, that is the optimal point. But we cannot say on the other side. But look at the two other corollaries. Those things a little bit, hint will give about those things. If primal is feasible and objective function is unbounded, then the dual problem cannot have a feasible solution. So look here what is happening. The primal is a feasible point, right? It's a feasible problem, and the objective function is unbounded. Then the dual problem cannot have a feasible solution. See, it is also obvious, because look here in this particular problem, that is the original problem, which is one of maximization. Suppose we have the same three constraints. We have the same three constraints. However, the objective function is unbounded. That means the objective function is not 600x1 plus 400x2, but it is of the form maybe infinity into x1 plus 400x2. That means that the objective function can be as big as possible. See, we have those constraints, that is true. But since the objective function is unbounded, what it may be possible is that the optimum solution cannot be found, because the maximum problem becomes higher and higher, because we have seen some problems in special cases where the solution space is unbounded, and the maximization problem. Therefore, the final solution, optimum solution, comes to at one point, infinity. So what happens that since it is the lower bound of the dual problem, the minimization problem, so what is happening? The minimization problem, the we do not have any bound, isn't it? So therefore we can say that if the primal is feasible and the objective function is unbounded, then the dual problem cannot have a feasible solution. By the same coin, if the dual is feasible and the objective function is unbounded, which is the minimization problem, then similarly on the same coin, the primal problem cannot have a feasible solution. So it is very important that the objective function should be bounded. So that's what we studied, the weak duality theorem. Once again, I'm reading it. For symmetric primal dual linear programs, the value of the objective function of the minimum problem for any feasible solution is always greater than or equal to that of the maximum problem, that is YB should be greater than equal to CX. And there are 4 corollaries which are connecting those problems with one another. Now, having said that, let us look at some more very important theorems. In fact, there are 3 others. The second one, optimality criteria theorem. So suppose it says that if there exist feasible solutions x0 and y0 for the symmetric primal dual linear programs such that corresponding values of their objective functions are equal, then these feasible solutions are in fact optimum solutions to their respective problems. So what was already known, it is actually stating it very, very clearly now, that if there exists feasible solutions x0 and y0 for the symmetric primal dual linear programs such that the corresponding values of their objective functions are equal, then these feasible solutions are in fact optimum solutions to their respective problems. Yes or not? So we have already seen this original problem, and we have seen their optimum solutions. So what exactly it says, that this is the primal problem. Suppose we do not know whether it is an optimum solution, and we also do not know whether it is an optimum solution, but we know that this is going to be a feasible point. That means this is the basic feasible solution that we know. We know that for the original problem, one basic feasible solution is x1 star equal to 60, x2 equal to 40, and z is 52,000. And for the dual problem also we know a feasible solution is y1 equal to 100, y2 equal to 100, and y3 equal to 0. And in that case, z is also 52,000. So we see that the original problem and the dual problem, they are feasible solutions and their objective function values are equal. So if that happens, then we can immediately say that look here, they are optimum solutions for the primal and the dual problem respectively, right? So having said that, let me read it once again. If there exist feasible solutions x0 and y0 for the symmetric primal dual linear programs such that corresponding values of their objective functions are equal, then these feasible solutions are in fact optimum solutions to their respective problems. In fact, if you follow the weak duality theorem and follow it clearly, then you can find out the optimality criteria theorem also very clearly. So they are all connected to one another. It simply says that if we simply find 2 feasible solutions of the primal and the dual and we find them as equal, then that particular solution has to be optimum. All right. So having said that, let's move over and to see the third theorem, that is the main dual theorem. The main dual theorem basically says if both the primal and dual problems are feasible, then they both have optimal solutions such that their optimal values of the objective functions are equal. So it is coming from the other side. The previous theorem we had come from the the solutions are feasible and equal, then they must be optimum. right? So if the solutions are feasible and they are equal, then they must be optimal. Here what we are saying, that if the primal and dual problems are feasible and they both have optimal solutions such that they are optimal, if they are feasible, then they have optimal solutions such that their optimal values of the objective functions are equal. So it is saying, simply saying that for if feasibility is maintained, then they will have optimal solutions and they will be equal. Right. So all these, weak duality theorem, the optimality theorem, and the main dual theorem, they are all images of one another. And we have to understand one thing, that if the primal and dual returns feasible solutions, then their optimal solutions become equal and at that point is very, very vital and important to find out. But let us now come to the most important topic of our discussions today, which is known as the complementary slackness theorem. The complementary slackness theorem essentially, you know, uh, states in this manner, which is slightly complicated to understand, that let x0 and y0 be feasible for the primal and the dual problems respectively. Then x0 and y0 are optimal to their respective problems if and only if y0a minus c into x0 plus y0 into b minus ax0 equal to 0. Look at this expression carefully. The primal problem is maximize z equal to cx subject to ax less than equal to b. So what is b minus ax0? B minus ax0 is nothing but equal to the slack variable. Can you see that? See, ax plus something equal to b. That would what would be your augmented problem, and that something is equal to the slack variable. So the slack variable value will be b minus ax, isn't it? And at that feasible point x0, that value should be b minus ax0. Similarly, in the dual case, if we have a dual surplus variable, that dual surplus variable ya plus that surplus variable equal to c. So what is that value of the surplus variable? It will be c minus ya, isn't it? Or it should be ya minus c because it is, sorry, it is minus, because it is minus, so it will go to the other side, and ya minus c will be equal to that surplus variable. But let us call slack in an uniform manner. So in this case, the b minus ax0 is like our primal slack and y0a minus c is like the dual slack, isn't it? So that complementary slackness theorem therefore can be expressed in this manner. If x0 and y0 be the feasible for the primal and the dual problems respectively, then x0 and y0 are optimal to their respective problems if and only if y0a minus c into x0 plus y0 into b minus ax0 equal to 0. So if u0 and v0 are slack variables for the primal and the dual problem respectively, then we have the v0 x0 plus y0 u0 equal to 0. Please mind, this is a vector equation. So is this vector equation clear? The vector equation essentially says that the x0 and y0 will be optimal only when this particular equation is satisfied. What is that equation? This equation is v0 x0, that is the dual slack multiplied by the primal variable and the primal slack multiplied by the dual variable together, they should be equal to 0. But since it's a vector equation, individually, if we look at their the individual scalar components, the scalar components will be then, that is what is mentioned here. So this part is already I have stated. So complementary slackness conditions therefore should be that Vj0 into xj0 will be 0 for all j equal to 1 to n, and yi0 into ui0 equal to 0 for all I equal to 1 to n. So because you see this is the vector part. Now this can be 0 only when when both v0 x0 and y0 u0 equal to 0 for individual scalar components, right? In other words, the vj0 xj0 should be equal to 0, and yj0 yi0 and ui0 should also be equal to 0. So that is the complementary slackness condition. Once again, let me read it out. Let x0 and y0 be the feasible for the primal and the dual problems respectively. Then x0 and y0 are optimal to their respective problems if and only if the v0 x0 plus y0 u0 equal to 0, which in a scalar statement is vj0 xj0 equal to 0 and yi0 ui0 equal to 0. Let us look at a very simple statement of the complementary slackness condition. A simple statement of the complementary slackness condition is that if at the optimal point the primal slack vanishes, that is, a primal constant turns to equality, then the corresponding dual variable exists in the basis. So what happens that if the primal slack vanishes, right? The primal slack in this case is your say u0 or u1, a particular one. So if that u1 becomes 0, then since u1 into y1 equal to 0, so therefore that dual variable will be having a value. It will exist in the basis. So in the other side, if the dual slack vanishes, the dual constant turns to equality, then the corresponding primal variable exists in the basis. So this is in a simple statement of the complementary slackness condition. Let us take this example once again. Look here. This is the original problem. In the original problem, the solution is, optimum solution is x1 star equal to 60 and x2 star equal to 40 and z star equal to 52,000. So what really happens, these x1 and x2, they are like dual variables to these two equations? Yes or no? See, x1 is the dual variable for this particular constraint, and x2 is the dual variable for this particular constraint. Now, if x1 exists in the basis, that means x1 equal to 60 and x2 equal to 40, they both have values. And we know very well that x1 star, the corresponding dual slack is 0. So if x1 has a value, that dual slack has to become 0. If x2 has a value, that dual slack has to become 0. So what will happen? The dual slack for this constraint is vanishing and dual slack for this constraint vanishing. Then what will happen to these two constraints? They will become equality. Can you see that? See, since x1 exists and x2 exists, so therefore this constraint will become equality at the optimal point. This constraint will also become equality at the optimal point. Also look at from the dual to the original. See, in the original solution, the dual y1 equal to 100, y2 equal to 100 and y3 equal to 0. So y1, y2, y3 are dual variables corresponding to these three constants. So in the first constraint, since y1 exists, this will turn to equality. Second constraint, y2 exists, so these will turn to equality. Third constraint, y3 does not exist because it has only a 0 value, so we cannot say anything about the third constraint. Is it all right? So you see, same thing is mentioned here. Look here, since x1 and x2 has values, note that as the dual variable exists, the primal slack has vanished and vice versa. So in this case, the primal variable has a solution, that is x1 and x2. They assume values, so these will turn to equality. And similarly here, since y1 and y2 has values y1 100 and y2 100, so these two have turned to equality, is it not? So this is the very interesting thing. So supposing I can solve the dual by a simple method, then by looking at the dual, I can make the certain thing about the primal thing. We can tell that these two constraints will turn to equality. Now, once we know that these two constraints have turned to equality, we can solve these two and we can find out that x1 equal to 60 and x2 equal to 40. Supposing, I have this primal and this dual, and somebody gives me the dual solution, that is 100, 100, 0. Then I can come back to the primal and we say that y1 exists, y2 exists. By complementary slackness condition, this constant turns to equality, this constant turns to equality. Then we can solve these two simultaneous equation and we can actually find x1 equal to 60 and x2 equal to 40. Is it clear what exactly we are telling and how we can actually make use of the complementary slackness condition? Is the concept clear to you? Why those two constraints are getting equal? Have you all understood that how this complementary slackness condition has actually worked? All right. So at the optimum point, not at all points, at the optimum point, y1, y2, y3 assume values. Out of that, y3 remains at 0. So since y1 and y2 have got non-zero values, we can immediately understand that these two constraints, they become equality. Now, this particular property of complementary slackness condition can actually be exploited and certain very important problems can be solved. Let us look at a particular example. So this problem you have already solved. If you recall, maximize z equal to x1 plus 2x2 minus x3 subject to 2x1 plus x2 minus 3x3 less than equal to 5, minus 4x1 minus x2 plus x3 less than equal to 4, and x1 plus 3x2 less than equal to 6. x1, x2, x3 are unrestricted in sign. So how to solve this problem? Forget the first line. How to solve this problem? What have you done? x1, x2, x3 are unrestricted in sign. So we have replaced x1, x2, x3 by y1 minus y2, y3 minus y4, and y5 minus y6. Yes or no? And then we replace them and it would be a 6 variable. And then we solve this problem by, the simplex method. Yes or no? Do you remember that? Yes, yes. So you have already solved this problem in a particular way. But now look at this particular problem can also be solved in a very different way by making use of complementary slackness condition. Solve the following linear programming problem by only inspecting its dual. One very interesting thing about this problem is x1, x2, x3, they are unrestricted in sign. Since they are unrestricted in sign, can you tell me what would be the signs of the dual constraints? They will be all equal to, is it not? So that we already know. So that is precisely what we have done. X1, x2, x3 are unrestricted in sign. Therefore, if we take its dual, the dual will be like this. First of all, what should be the dual? The three dual variables are y1, y2, y3. So objective function will be 5y1 plus 4y2 plus 6y3, and it should be a minimization problem, right? And thereafter we know that 2y1 minus 4y2 plus y3 equal to 1. Then y1 minus y2 plus 3y3 equal to 2, and minus 3y1 plus y2 equal to minus 1. This equal to is coming because x1, x2, x3 are unrestricted in sign. And since the maximization problem standard form constants are there, therefore we say that y1, y2, y3 are greater than equal to 0. So this is our dual problem. Now, can you solve this dual problem? This dual problem will be easy to solve because after all there are three unknowns and there are three equality constraints. Is it not? So all we have to do is we have to solve these three equations. We have to solve these three equations in the usual way, and we can find out the solutions for y1, y2 and y3. So precisely this is what we have done. So by I mean, you know all those, but let just quickly to show you. See, these are 2y1 minus 4y2 plus y3 and y1 minus y2 plus 3y3. So if you multiply this first by 3 times, then it will be 3y3, then 3y3, and then deduct the number 2. So 3y3 will be cancelled, and therefore it will be 6y1 minus y1, that is 5y1, and this will be minus 11y2 will be equal to 1, isn't it? So, and if you multiply this third equation by 11 times, then minus 33y1 plus 11y2 equal to minus 11. These two we can add, and then we can get minus 28y1 equal to minus 10. So we can obtain y1 equal to 5 by 14. And these we can put in number 3, and therefore we can get y2 equal to 1 by 14. Putting in 2 we get, and from 2 then, because already we have found y1 and y2, we can find y3, which is 8 by 14. So we know that y1 equal to 5 by 14, y2 equal to 1 by 14, y3 equal to 8 by 14, and y equal to 5 times this, 4 times this, and 6 times this equal to 11 by 2. So we already solved by dual by inspection, right? So dual problem has become easy to solve, and we have already solved the dual problem, and we found some solutions of dual. What is important that each of these y1, y2 and y3 exist. Now look at this equation in the primal and tell me what is your conclusion from this solving the dual problem. Please look at it carefully. After solving the dual, we found that y1, y2, y3, all of them, they exist and they assume specific values, right? They are non-zero values. Each y1, y2, y3, they become non-zero values. So what is the complementary slackness condition says? That y1 multiplied by the corresponding slack at the optimal point equal to 0. That means the slack will vanish because y1 exists. Similarly, y2 exists, so this slack will also vanish. y3 exists, so this slack will also vanish. In other words, since y1, y2, y3, they all exist, we can conclude that these three constraints will now then turn to equality. Isn't it? So those three will now turn to equality. So the primal problem, these are the dual solutions. Y1 star equal to 5 by 14, 1 by 14 and 8 by 14. Since all the dual variables exist in the optimal solution, we can infer by complementary slackness condition that all the primal slack will vanish at the optimal point. Isn't it? So therefore, at the optimal point, all the primal constraints will turn to equality. So therefore, all of them will be equality, and that is what we have written. So look here, 2x1 plus x2 minus 3x2 equal to 5, minus 4x1 minus x2 plus x3 equal to 4, and x1 plus 3x2 equal to 6. So they will all have turned to equality, and then by the method of elimination, because we can 3 times of if we can add this with the 1, and we can get minus 10x1 minus 2x2 equal to 17, and 10 times 3 will also give 10x1 plus 30x2 equal to 60. By adding them, 28x2 should be 77, and therefore x2 equal to 11 by 4. And by substitutions, we can get x1 star equal to minus 9 by 4, x2 star equal to 11 by 4, and x3 star equal to minus 9 by 4, and z star equal to 11 by 2. So very interesting thing, look here, what exactly we did. All we did is we took the dual. The dual problem was easy to solve, and that particular dual thing helped us into making some conclusions about the primal by the complementary slackness condition, which actually states if the primal if the dual variable exists, then the primal slack will vanish. So there are many ways of saying it. All we know is that dual slack into primal variable and primal slack into the corresponding dual variable equal to 0 at the optimal point. Yes or not? So with that knowledge, we can make number of inferences. We can solve the dual, tell something about the primal, solve the primal, tell something about the dual. And by comparing these two problems, we can solve a lot of very interesting problems. So because see, this is a problem that we have solved, which is simple problem. But there could be situations where the problem is much more complicated to look at. But after you take its dual and inspect the dual, you will find the dual to be much easier to solve. And by the dual solutions, you can say certain things about the primal, and you can then solve the primal also in a relatively easy manner. One such very important are the network related problems. The network problems actually, can be solved in a very interesting manner, and there is a method called the network simplex method. The network simplex method essentially, the dual, if you take the dual of the particular thing, the dual actually represents the node potentials, but we shall discuss all those things slightly later. And all the important thing that are important to us is that we can also solve many other very interesting problems, including the transportation problem. We can get certain help by taking help of the complementary slackness condition, right? So that is about today, and we shall take more examples of dual problems tomorrow, right? So thank you very much.